Tonight, we're going to talk about the supermassive black hole at the heart of our galaxy, Sagittarius A. 4 million times the mass of our Sun, sitting 26,000 light-years away, buried behind an impenetrable wall of cosmic dust that has hidden it from our view for all of human history. For decades, we've known it was there, watching stars whip around it at impossible speeds, seeing the evidence of its gravity, but never able to see what was happening in the region around it. Then the James Webb Space Telescope turned its infrared eyes toward the galactic center, and what it found defies every prediction we had. Stars forming where nothing should survive. Water molecules existing in conditions that should vaporize them instantly. Mysterious gas glowing with no apparent energy source. Evidence of black holes within black holes that could rewrite our understanding of how these cosmic monsters grow. By the end of tonight, you're going to understand why astronomers are calling these observations the most important black hole discoveries in decades, and why they're forcing us to rewrite the textbooks on how galaxies evolve, how stars form, and what's really happening in the most extreme environments in the universe. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now, let's begin. Sagittarius A sits at the exact center of our galaxy. It's the gravitational anchor point around which every single star in the Milky Way orbits, including our own Sun, which circles this black hole once every 225 million years. We've known about Sagittarius A for decades. Astronomers discovered it by tracking stars near the galactic center, watching them whip around an invisible point at speeds that seemed impossible. These observations began in the 1990s, when astronomers at the Keck Observatory in Hawaii started monitoring individual stars in the galactic center. They gave these stars simple names: S1, S2, S3, and so on. The S stands for source, and the numbers were assigned in the order they were discovered. One star, called S2, became particularly famous. S2 completes an orbit around Sagittarius A every 16 years, reaching speeds of 5% the speed of light at its closest approach. That's over 9 million miles per second. The gravitational forces are so immense that time literally runs slower for S2 when it's close to the black hole, and light from the star is gravitationally redshifted by the intense gravity. Astronomers have measured these effects precisely, and they match Einstein's predictions perfectly. The only way to explain that motion was a supermassive black hole, sitting right there at the center of everything. By tracking dozens of stars like this over years and decades, astronomers determined the black hole's mass with remarkable precision: 4 million solar masses. In 2022, the Event Horizon Telescope gave us the first direct image of Sagittarius A, showing the glowing ring of superheated gas around the black hole's event horizon. The image showed a dark circle, the black hole's shadow, surrounded by a bright ring of glowing gas. This ring is the inner edge of the accretion disk, the swirling disk of material orbiting the black hole. The gas in this disk is heated to millions of degrees by friction and compression, causing it to emit intense radiation. The dark circle in the center is not the black hole itself, which is infinitely small according to general relativity, but the event horizon, the point of no return. It was a triumph of astronomy, proof that Einstein's predictions about black holes were correct. Once something crosses the event horizon, it cannot escape, no matter what, not even light. But here's what nobody expected. The Event Horizon Telescope could only see the black hole itself, the immediate environment right around the event horizon. It couldn't see what was happening farther out because that region is completely obscured by dust. 26,000 light-years of cosmic dust sits between us and the galactic center, made of tiny particles created in dying stars and scattered into space. Visible light can't penetrate it. Radio waves can, which is how the Event Horizon Telescope imaged the black hole. But radio observations have low resolution and can't show fine details. Infrared light, on the other hand, passes through dust almost as if it weren't there. And that's where the James Webb Space Telescope comes in. Webb is the most powerful infrared telescope ever built. It launched in December 2021 and became fully operational in mid-2022, after a complex commissioning period where its mirrors were aligned and instruments calibrated. Webb's mirror is 21.3 feet across, nearly 3 times the diameter of Hubble's mirror. A larger mirror collects more light, allowing the telescope to see fainter objects at greater distances. And Webb is specifically designed to observe the universe in infrared wavelengths, from near-infrared, barely longer than visible light, all the way to mid-infrared, deep into the heat spectrum. This infrared vision is what allows it to see through the dust that has hidden the galactic center from us for all of human history. For the first time, we could look through the cosmic veil and see what's really happening around Sagittarius A. And what Webb saw shocked everyone. Let's start with the most impossible discovery: young stars. Stars forming in the immediate vicinity of the black hole, in a region where physics says star formation should be completely impossible. Star formation requires cold, dense gas clouds. When a cloud of gas collapses under its own gravity, it fragments into clumps, and those clumps continue collapsing until their cores become hot enough for nuclear fusion to ignite. That's how stars are born. The process starts with molecular clouds, vast regions of space filled with hydrogen and helium gas, along with trace amounts of heavier elements and dust. These clouds can be hundreds of light-years across and contain enough material to make millions of stars. But most of the time, they're stable. The internal pressure of the gas balances out the inward pull of gravity, preventing collapse. For a cloud to start collapsing, something has to disturb it. Maybe a nearby supernova explodes, sending a shock wave through the cloud that compresses parts of it. Maybe 2 clouds collide, increasing the density. Or maybe the cloud just becomes so massive that gravity eventually overwhelms the pressure. Once collapse begins, the cloud fragments. Dense regions within the cloud collapse faster than the surrounding material, creating distinct clumps. These clumps continue to collapse, and as they do, they heat up. Gravitational potential energy is converted into thermal energy. Eventually, the core of a collapsing clump becomes hot enough for nuclear fusion to begin, typically around 10 million degrees Fahrenheit. At that temperature, hydrogen nuclei have enough energy to overcome their electromagnetic repulsion and fuse together, forming helium and releasing energy. When fusion ignites, a star is born. The energy released by fusion creates an outward pressure that balances gravity, stabilizing the star. From that point on, the star will spend most of its life in a stable state, fusing hydrogen into helium in its core. But the environment around a black hole is nothing like that. It's a radiation hell. The gas, falling towards Sagittarius A, forms an accretion disk, a swirling disk of superheated material orbiting at nearly the speed of light. As gas spirals inward, it rubs against neighboring gas, creating friction. This friction heats the gas to millions of degrees. At these temperatures, the gas glows brightly, emitting radiation across the entire electromagnetic spectrum, from radio waves to X-rays. This disk emits intense X-rays and ultraviolet radiation. Any nearby gas clouds should be heated and ionized by this radiation, preventing them from collapsing. When high-energy photons, like X-rays or ultraviolet light, hit a gas cloud, they transfer energy to the gas atoms. This energy can knock electrons off the atoms, ionizing them. Ionized gas is hot gas. The free electrons and ions have a lot of kinetic energy, moving at high speeds and bouncing off each other. This thermal energy creates pressure that resists gravitational collapse. In other words, radiation from the accretion disk should heat any nearby gas clouds to the point where they can't collapse to form stars. The tidal forces from the black hole's gravity should also rip apart any gas clouds before they can collapse. Tidal forces arise because gravity gets weaker with distance. One side of a gas cloud is closer to the black hole than the other, so it feels a stronger gravitational pull. This difference stretches the cloud, pulling it apart. Near a supermassive black hole, tidal forces are enormous. For Sagittarius A, the tidal forces become strong enough to disrupt a gas cloud at a distance of about 1 light-year from the black hole. Inside that radius, any gas cloud should be stretched and torn apart before it can collapse. For all these reasons, astronomers have believed for decades that star formation near a supermassive black hole should be impossible. The region within a few light-years of the black hole should be sterile, a cosmic wasteland where nothing new can form. But Webb found hundreds of young stars in that exact region. Not old stars that wandered in from elsewhere, but young, hot, massive stars that clearly formed recently, within the last few million years. Some of them are less than 1 million years old, practically newborns in astronomical terms. To put that in perspective, these stars formed around the same time that early humans were beginning to walk upright on the plains of Africa. In cosmic terms, that's yesterday. These stars are so young that they're still surrounded by the dusty disks from which they formed. When a star forms, not all of the collapsing gas ends up in the star itself. Some of it forms a disk around the star, a protoplanetary disk. Over time, this disk can coalesce into planets, moons, asteroids, and comets, or it can be blown away by the star's radiation. The presence of these disks around the young stars near Sagittarius A tells us that the stars formed in place, not elsewhere in the galaxy. If they had formed far from the black hole and then migrated inward, their protoplanetary disks would have been stripped away long ago by interactions with other stars or by the harsh radiation environment near the black hole. The fact that the disks are still there means the stars must have formed recently and locally. And they're massive, tens of times the mass of our Sun, which means they formed quickly and violently. Massive stars live fast and die young. They burn through their nuclear fuel in just a few million years, compared to the 10 billion-year lifespan of a star like our Sun. The fact that there are massive young stars near Sagittarius A tells us that star formation has been happening there recently and probably continues to happen now. How is this possible? Nobody knows. The leading theory, proposed after these observations, is that the gas around the black hole somehow managed to collapse into a disk, a dense, rotating structure that was stable enough to shield itself from the black hole's radiation. Within this disk, the gas could cool down and fragment, allowing stars to form. The idea is that the disk itself would be thick enough and dense enough to absorb the radiation from the inner accretion disk, preventing it from heating the outer parts of the disk. In the shielded, cooler regions of the disk, gas could collapse and form stars. But this theory has problems. Simulations show that such a disk would be unstable. The black hole's gravity would create spiral density waves in the disk, regions where gas piles up temporarily. These waves can trigger fragmentation and star formation, but they also transport angular momentum, causing gas to either fall inward toward the black hole or spread outward away from it. The disk would either fall into the black hole or be torn apart by tidal forces within a few thousand years, not nearly long enough for stars to form. Star formation takes at least a few 100,000 years, and often longer. A gas cloud has to collapse, fragment, and then the individual clumps have to collapse further until fusion ignites. This process is slow because the collapsing gas radiates away energy, and without getting rid of energy, the gas can't collapse. Radiation is the main cooling mechanism, and it takes time. For a disk around Sagittarius A to survive long enough for stars to form, it would need to be much more stable than simulations predict. Maybe there's some mechanism that stabilizes the disk, something we're not accounting for in our models. Maybe magnetic fields play a role, threading through the disk and providing additional support against gravitational collapse. Or maybe the disk is continuously replenished with new gas, maintaining its structure even as some gas falls inward and some spreads outward. But we don't know. The observations tell us that stars are forming, but the theory doesn't yet explain how. And yet, the stars are there. They exist. Physics says they shouldn't, but observation says they do. This is the paradox Webb has handed us. A cosmic fertility in an environment that should be a sterile graveyard. It gets stranger. Webb didn't just find a few stars scattered around the black hole. It found an entire population of stars that nobody knew existed. Hundreds of them, maybe more, once all the data is fully analyzed. Previous observations from ground-based telescopes, and even Hubble, had detected some stars near the galactic center, but they could only see the brightest, most massive ones. The galactic center is so crowded with stars, and the dust obscures so much that only the very brightest stars stood out clearly. Everything else was lost in the glare. Webb's infrared vision revealed a whole population of smaller, cooler stars that had been completely invisible until now. Infrared light penetrates dust, as I mentioned, but it also allows us to see cool objects that don't emit much visible light. Red dwarf stars, for example, are small, cool stars that emit most of their light in the infrared. They're incredibly common in the galaxy, making up about 70% of all stars, but they're difficult to see in visible light because they're so faint. Webb's instruments are sensitive to these cool stars, revealing them in large numbers near Sagittarius A. Some of these stars are red giants, old stars in the late stages of their lives. Red giants form when a star like our Sun exhausts the hydrogen fuel in its core. The core contracts and heats up, while the outer layers expand dramatically, becoming cool and red. Red giants are bright in infrared light because of their large, cool surfaces. Others are main sequence stars, similar to our Sun but older. These stars are quietly fusing hydrogen in their cores, stable and unremarkable, except for the fact that they're in one of the most extreme environments in the galaxy, and many of them are in places where they shouldn't be. They're orbiting the black hole in chaotic, eccentric orbits that don't match the orderly rotation of the rest of the galaxy. In most of the galaxy, stars orbit in roughly circular paths, all moving in the same direction around the galactic center, like cars on a highway. This orderly motion is a result of the galaxy's formation. When the Milky Way formed billions of years ago, it started as a rotating cloud of gas. As the cloud collapsed, it flattened into a disk, and the stars that formed within that disk inherited the cloud's rotation. But the stars near Sagittarius A don't follow this pattern. Their orbits are all over the place, tilted at different angles, elongated into highly eccentric ellipses, moving in different directions. This suggests they've been gravitationally scattered, thrown into weird orbits by close encounters with other stars or by the black hole itself. When two stars pass close to each other, they can exchange energy and angular momentum through their gravitational interaction. One star might speed up and be flung into a wider orbit, while the other slows down and falls closer to the black hole. These interactions are rare in most of the galaxy because stars are so far apart, but near the galactic center, where the density of stars is millions of times higher than in our neighborhood, close encounters happen regularly. Over time, these encounters randomize the orbits of stars, creating the chaotic distribution Webb observed. It's a violent, chaotic environment, and these stars are the survivors. They've been playing a cosmic game of pinball for millions of years, bouncing off each other's gravitational fields, and they're still here. But some stars aren't so lucky. Every so often, a star passes too close to Sagittarius A and gets tidally disrupted, torn apart by the black hole's gravity. When this happens, the star is stretched into a long stream of gas, which then spirals into the accretion disk. The black hole feeds, and for a brief period, it becomes much brighter as the star's material is consumed. These events are called tidal disruption events, and they're rare, happening perhaps once every few thousand years for a black hole like Sagittarius A. But when they do happen, they're spectacular, releasing enormous amounts of energy. Now, let's talk about the gas. Webb detected clumpy structures in the gas around Sagittarius A, dense knots of material spiraling inward toward the event horizon. This was expected. Gas falling into a black hole doesn't fall straight in. It spirals, forming an accretion disk, and within that disk, instabilities can create clumps. These instabilities arise because the disk is turbulent. Gas, orbiting at different distances from the black hole, moves at different speeds, with the inner gas orbiting faster than the outer gas. This differential rotation creates shear, which in turn generates turbulence. Turbulence creates eddies and vortices, regions where gas piles up temporarily before being dispersed again. Some of these density fluctuations can grow, pulling in more gas and becoming denser, creating clumps. But what wasn't expected was how organized these clumps are. They're not random. They appear to be forming a spiral pattern, like the arms of a spiral galaxy, but on a much smaller scale. Spiral patterns in accretion disks are thought to arise from density waves, ripples in the disk that propagate outward from the black hole. These waves are created by the gravitational influence of the black hole itself, or possibly by the influence of a massive object within the disk, like a star or a smaller black hole. As the density wave moves through the disk, it compresses the gas, creating regions of higher density that appear as spiral arms. This spiral structure is being driven by the black hole's gravity, but the details of how it forms and stays stable are unclear. In principle, Spiral density waves should be transient, forming and then dissipating as the gas moves around. But the spiral structure Webb observed appears to be persistent, suggesting that something is continuously driving it. Maybe there's a massive object embedded in the disk, orbiting the black hole and creating a gravitational wake that organizes the gas into spirals. Or maybe the disk is interacting with magnetic fields in a way that stabilizes the spiral pattern. We don't know. The clumps are also moving fast, orbiting the black hole at significant fractions of the speed of light. At the inner edge of the accretion disk, just outside the event horizon, gas is moving at about 30% of the speed of light. That's about 55,000 miles per second. At these speeds, relativistic effects become important. Time dilation, length contraction, and the increase in mass with velocity all come into play. The gas in the inner disk is experiencing a gravitational field so strong and moving so fast that Einstein's general relativity is essential to understanding its behavior. And as they spiral inward, they're heating up, emitting intense radiation. The friction and compression heat the gas to millions of degrees. At these temperatures, the gas emits X-rays and ultraviolet light. This radiation carries energy away from the disk, allowing more gas to fall inward. Without radiation to carry away energy, the gas would heat up until the pressure balanced the inward pull of gravity and it would stop falling. But radiation provides a cooling mechanism, allowing the gas to continue its inward spiral. This is the fuel for the black hole. When Sagittarius A is actively feeding, when it's pulling in large amounts of gas, it becomes what astronomers call an active galactic nucleus. The accretion disk glows brightly, outshining all the stars in the galaxy combined. In some galaxies, active galactic nuclei are so bright that we can see them from billions of light years away. These are quasars, the brightest objects in the universe. But right now, Sagittarius A is dormant. It's not feeding. Or more accurately, it's feeding at a very low rate, consuming only a tiny fraction of the gas that's available. The clumps of gas Webb observed are there, spiraling inward, but they're not falling in at a high rate. Most of the gas is being blown away by stellar winds from nearby stars, or heated by radiation and dispersed before it can reach the event horizon. The black hole is surrounded by fuel, but it's barely eating. Why? This is one of the biggest mysteries about supermassive black holes. They don't feed continuously. They go through cycles, periods of intense activity, followed by long dormant phases. During an active phase, the black hole consumes vast amounts of gas, growing rapidly and releasing enormous amounts of energy. The accretion disk becomes incredibly bright, and powerful jets of matter and energy can shoot outward from the poles of the black hole, extending for thousands of light years into space. These jets are created by magnetic fields in the accretion disk. As gas spirals inward, it drags magnetic field lines with it, twisting and tangling them. Eventually, the magnetic field becomes so twisted that it releases energy in the form of jets, blasting gas outward at nearly the speed of light. These jets can have profound effects on the galaxy, heating gas and preventing it from cooling and forming stars. During a dormant phase, like the one Sagittarius A is in now, the black hole barely feeds at all. The accretion disk is faint, the jets shut off, and the black hole's influence on the galaxy is minimal. What triggers the transition between these phases? Nobody knows for sure. One possibility is that the supply of gas varies. Maybe there are periods when a lot of gas is available, perhaps from a nearby star being tidally disrupted, or from a gas cloud wandering too close. and periods when there's not much gas around. When gas is abundant, the black hole feeds voraciously, growing and releasing energy. When gas is scarce, the black hole goes dormant. Another possibility is that the black hole's own activity regulates its feeding. When the black hole is actively feeding, it produces powerful jets and winds that blow gas away from the accretion disk. This is called AGN feedback, active galactic nucleus feedback. The jets and winds heat the surrounding gas, preventing it from cooling and falling into the black hole. This feedback can shut off the gas supply, causing the black hole to become dormant. Then, over time, gas accumulates again, eventually reaching a threshold where it overcomes the feedback and starts falling in. The cycle repeats. This self-regulating behavior could explain why supermassive black holes cycle between active and dormant states. But the details are unclear. We don't know what determines the timescale of these cycles, or what fraction of the time a black hole spends in each phase. Webb found evidence of past activity. By analyzing the light from gas clouds far from the black hole, astronomers discovered that these clouds are glowing in a specific way that indicates they were recently hit by a burst of intense radiation. The gas in these clouds is ionized, meaning the atoms have been stripped of their electrons. This ionization requires energy, and the most likely source is radiation from Sagittarius A. But here's the interesting part. The gas clouds are located several light years from the black hole. If Sagittarius A emitted a burst of radiation, it would take several years for that radiation to reach these clouds, traveling at the speed of light. By measuring the properties of the glowing gas and calculating how long it would take for the radiation to travel from the black hole to the gas clouds, astronomers determined that Sagittarius A experienced a major outburst about 300 to 400 years ago. Sometime in the 1600s or 1700s, our galaxy's central black hole was actively feeding, shining brightly, pumping out intense X-rays and ultraviolet light. Then it shut off. And now, in the early 21st century, it's dormant. The light from that outburst has long since faded, but the gas clouds it ionized are still glowing, a cosmic echo of the black hole's past violence. What caused that outburst? What caused it to end? And when will the next one happen? These are open questions, but the evidence is clear. Sagittarius A is not a stable, unchanging object. It's dynamic, cycling between active and dormant states on timescales of centuries. This has implications for the galaxy as a whole. When the black hole is active, its radiation can affect star formation across the entire galactic center, heating gas and preventing it from collapsing. The jets can sweep through the galaxy, creating bubbles of hot gas that persist for millions of years. When it's dormant, star formation can proceed more easily. The black hole's activity cycles might regulate the evolution of the galaxy itself, determining when and where stars form and shaping the structure of the galactic center. This is a new realization. For a long time, astronomers thought of black holes as passive objects that just sit there, pulling in whatever happens to wander too close. But we're learning that black holes are active players in galactic evolution. They don't just respond to their environment, they shape it. Now, let's talk about the most shocking discovery of all: water. Webb detected water molecules in the gas around Sagittarius A. This seems impossible. Water is a fragile molecule. It's made of 2 hydrogen atoms and 1 oxygen atom, bonded together in a bent configuration. The bonds between the atoms are relatively weak, held together by the electromagnetic force between the positively charged hydrogen nuclei and the negatively charged electrons shared between the atoms. In normal environments, like on Earth, water is stable. The bonds are strong enough to hold the molecule together under typical conditions of temperature and radiation. But in the extreme radiation environment around a black hole, water molecules should be destroyed instantly. The intense ultraviolet light and X-rays from the accretion disk should break the molecular bonds, tearing the water apart into individual atoms. When a high-energy photon hits a water molecule, it can transfer enough energy to break one of the bonds, splitting the molecule into hydrogen and oxygen atoms. This process is called photodissociation, and it happens very quickly in environments with intense ultraviolet radiation. Near Sagittarius A, the radiation field is so intense that water molecules should be photodissociated in less than a second. And yet, Webb found water. Not a lot, but it's there. Detectable in the infrared spectrum, Webb's instruments can identify molecules by their spectral signatures. Different molecules absorb and emit light at specific wavelengths, creating a unique pattern that acts like a fingerprint. Water has a distinctive infrared signature, with absorption lines at wavelengths of about 2.7 microns, 6.3 microns, and longer. Webb detected these signatures in the gas around Sagittarius A, confirming the presence of water molecules. How is it surviving? The leading explanation is that the water is forming continuously. Hydrogen and oxygen atoms in the gas around the black hole are constantly colliding and bonding to form water molecules. These molecules are then destroyed by radiation, but new ones form to replace them. There's a constant cycle of formation and destruction, and at any given moment, some water molecules exist in the gas. This is called chemical equilibrium. The rate of formation equals the rate of destruction, so the total amount of water stays roughly constant over time. But even this explanation has problems. The rate of destruction should be much faster than the rate of formation, meaning there shouldn't be enough water to detect. For water to form, a hydrogen atom and an oxygen atom have to collide with just the right energy and orientation to bond together. This is a relatively rare event, especially in the diffuse gas around a black hole, where atoms are spread out and moving at high speeds. Once a water molecule forms, it should be destroyed almost immediately by the intense radiation. The fact that Webb can see water molecules suggests that either the radiation environment is less intense than we thought, or there's some mechanism shielding the water from radiation. Maybe the water is forming in dense clumps of gas where the molecules are protected from the surrounding radiation. Dense gas can absorb radiation, shielding the molecules deeper inside the clump. If the clumps are dense enough and large enough, water molecules in the interior might survive for longer periods before being destroyed. Or maybe our models of the radiation environment are wrong. Maybe the accretion disk isn't emitting as much ultraviolet radiation as we calculated, or maybe the radiation is being absorbed or scattered by dust before it reaches the water molecules. Either way, it's a puzzle. The presence of water in such a hostile environment tells us that chemistry can happen in places we thought were too extreme. It suggests that even in the chaotic, violent region around a black hole, complex molecules can exist, at least temporarily. This has implications for astrobiology. If water can survive near a supermassive black hole, even in small amounts, it raises the question of whether other complex molecules could exist there too. Could organic molecules, the building blocks of life, form in such environments? Organic molecules are carbon-based compounds, like methane, formaldehyde, and amino acids. They're essential for life as we know it, forming the structures of cells, DNA, and proteins. On Earth, organic molecules are produced by living organisms, but they can also form through non-biological processes in space. Astronomers have detected organic molecules in molecular clouds, in the atmospheres of planets, and even in comets and asteroids. Could they form near a black hole? Almost certainly not. The radiation environment is just too harsh. Organic molecules are even more fragile than water, and they would be destroyed even faster. But the fact that we're even asking the question shows how much these observations have expanded our understanding of what's possible in extreme environments. A few years ago, the idea of finding any molecules near a black hole would have seemed absurd. Now we're detecting water and wondering what else might be there. Then there's the mystery of the ionized gas. Webb detected vast clouds of gas around Sagittarius A that are glowing brightly in infrared light. This glow indicates that the gas is ionized, meaning the atoms have been stripped of their electrons. When an atom loses one or more electrons, it becomes an ion, a charged particle. Ionized gas behaves differently than neutral gas. It conducts electricity, responds to magnetic fields, and emits radiation at specific wavelengths corresponding to the energy levels of the ion. By analyzing the spectrum of the glowing gas, astronomers can determine its temperature, density, and composition. Ionization requires energy. Something has to hit the gas with enough energy to knock electrons off the atoms. In most cases, this energy comes from radiation, usually from nearby stars or from the black hole itself. High-energy photons, like X-rays or ultraviolet light, can ionize gas by transferring energy to the atoms. When a photon hits an atom, it can knock an electron free, ionizing the atom. But in this case, there's no obvious energy source. The gas clouds Webb observed are far from any bright stars, and Sagittarius A is currently dormant, not producing much radiation. The nearest bright stars are several light-years away, too far to ionize these particular gas clouds. And the black hole's accretion disk, while it does emit some radiation, is currently so faint that it shouldn't be able to ionize gas at these distances. So where is the energy coming from? One possibility is that the gas was ionized in the past, during Sagittarius A's last active phase, 300 to 400 years ago, and it's still glowing now. Ionized gas can stay ionized for a long time if the density is low enough. When a gas is ionized, the free electrons and ions can recombine, with the electrons returning to the atoms and neutralizing the charge. But recombination takes time, and in very diffuse gas, where atoms and electrons rarely encounter each other, it can take thousands or even millions of years. If the gas Webb observed was ionized during the black hole's last outburst, and the density is low enough, it could still be ionized today, glowing faintly as the electrons slowly recombine with the ions. But this doesn't fully explain the observations. Some of the glowing gas is in regions that shouldn't have been affected by the black hole's past activity, too far away or in the wrong locations. Radiation from the black hole spreads outward in all directions, but it gets weaker with distance. By the time the radiation from Sagittarius A's outburst reached some of these gas clouds, it should have been too weak to ionize them. Another possibility is that there's a hidden energy source, something we haven't detected yet. Maybe there are hot, young stars embedded in the gas clouds, stars that are too faint or too obscured by dust for even Webb to see clearly. Young, massive stars emit intense ultraviolet radiation, which can ionize the surrounding gas. If there are such stars hiding in the gas clouds, they could be the energy source we're looking for. Or maybe there are shocks in the gas, regions where gas clouds are colliding at high speeds, generating heat and ionizing the atoms. Shocks occur when gas moving at different speeds collides. The collision converts kinetic energy into thermal energy, heating the gas. If the gas is heated enough, it becomes ionized. Shocks can occur when gas is falling toward the black hole, or when stellar winds from nearby stars collide with each other, or when supernova explosions push gas outward into the surrounding medium. All of these mechanisms could potentially ionize gas near Sagittarius A, but none of these explanations fully account for all the observations. The distribution of ionized gas, its temperature, and its spectrum don't perfectly match any single mechanism. It's possible that multiple processes are at work, each ionizing different regions of gas in different ways. The ionized gas remains a mystery, one that will require more observations and better models to solve. Now, let's talk about intermediate mass black holes. This might be the most important discovery Webb has made. It might be the discovery that changes everything we thought we knew about how supermassive black holes form and grow. Among the stars and gas clouds around Sagittarius A, Webb detected several objects that don't fit the profile of normal stars. They're too compact, too massive, and they're affecting the orbits of nearby stars in ways that suggest they have strong gravitational fields. These objects are dark. They don't emit much light, which is unusual for stars. Most stars shine because they're fusing hydrogen in their cores, converting mass into energy through nuclear fusion. Even the coolest, faintest stars, like red dwarfs, emit a detectable amount of light in the infrared. But these objects are darker than they should be if they were stars. They're also too massive to be planets or brown dwarfs. Brown dwarfs are failed stars, objects that formed like stars but never became massive enough to sustain hydrogen fusion. They're typically between 13 and 80 times the mass of Jupiter, which translates to roughly 0.01 to 0.08 times the mass of the Sun. Brown dwarfs are cool and faint, but they're still detectable in the infrared because they emit heat left over from their formation. The objects Webb detected are far more massive than brown dwarfs could be, and they're affecting the orbits of nearby stars in ways that indicate significant gravitational pull. When a massive object passes near a star, its gravity tugs on the star, changing its trajectory slightly. This is called gravitational perturbation, and it's one of the main ways astronomers detect dark objects like black holes. When astronomers track the orbits of stars near the galactic center, they can detect small deviations from the expected paths. These deviations indicate the presence of additional mass, something that's pulling on the stars gravitationally, but not emitting enough light to be seen directly. The technique works like this. First, astronomers observe a star's position multiple times over months or years, carefully measuring where it is in the sky. Then they calculate what the star's orbit should look like, based on the gravitational pull from Sagittarius A and the other visible stars nearby. If the star is moving exactly as predicted, the observations match the calculations perfectly. But if there's an invisible massive object nearby, the star's actual position will differ slightly from the predicted position. The star will be pulled slightly off course by the hidden object's gravity. By measuring these deviations precisely, astronomers can infer the presence of the hidden object, estimate its mass, and even determine roughly where it is. This is exactly how Neptune was discovered in 1846. Astronomers noticed that Uranus wasn't following its predicted orbit. something was pulling on it, perturbing its motion. By analyzing the deviations, they calculated where the hidden planet must be, and when they pointed their telescopes at that location, they found Neptune. The same principle applies to detecting black holes near Sagittarius A, except the deviations are much smaller and harder to measure because the stars are so far away. In most cases, this hidden mass is dark matter, or perhaps faint stars that are too dim to detect. Dark matter is the mysterious substance that makes up about 85% of all matter in the universe. It doesn't emit, absorb, or reflect light, so we can't see it directly. We only know it exists because of its gravitational effects. Galaxies rotate too fast to be held together by the gravity of visible matter alone. There must be additional mass, providing extra gravitational pull, and that mass is dark matter. Near the galactic center, dark matter should be present in significant quantities, and it could account for some of the gravitational perturbations Webb observed. Faint stars are another possibility. Not all stars are bright and easy to see. Old, cool stars called red dwarfs are incredibly faint, and if they're far away or obscured by dust, even Webb might struggle to detect them. But in some cases, the deviations are too large to be explained by dark matter or faint stars. The hidden objects must be very massive and very compact. The deviations observed by Webb suggest objects with masses ranging from a few hundred to a few thousand times the mass of the Sun, all concentrated in regions too small to be normal stars or clusters of stars. The only objects that can pack that much mass into such a small volume are black holes. The most likely explanation is that these objects are black holes, not stellar mass black holes formed from the collapse of individual stars, but intermediate mass black holes with masses ranging from a few hundred to a few thousand times the mass of the Sun. This is huge. Intermediate mass black holes have been theorized for decades, but they've been incredibly difficult to detect. We know stellar mass black holes exist, formed when massive stars collapse. When a star with a mass greater than about 20 times the Sun's mass exhausts its nuclear fuel, its core collapses under gravity. If the core is massive enough, more than about 3 solar masses, the collapse can't be stopped by any known force. The core collapses to a point, forming a black hole. These stellar mass black holes range from about 3 times the Sun's mass to maybe 100 times the Sun's mass. We've detected many of them, either by observing their gravitational effects on companion stars, or more recently, by detecting gravitational waves from merging black holes. We also know supermassive black holes exist, like Sagittarius A, with masses ranging from millions to billions of times the Sun's mass. Nearly every large galaxy has a supermassive black hole at its center. We've observed thousands of them across the universe, from nearby galaxies to distant quasars, billions of light-years away. But how do supermassive black holes form? How do you get from a 100 solar mass black hole to a 4 million solar mass black hole? And more importantly, how do you get to a billion solar mass black hole in less than a billion years after the Big Bang? This is one of the biggest unsolved questions in astrophysics. The most popular theory is that supermassive black holes grow by accreting gas and by merging with other black holes. Start with a stellar mass black hole, let it consume gas for billions of years, and occasionally merge it with other black holes, and eventually you get a supermassive black hole. This sounds reasonable, but when you actually do the math, problems emerge. Black holes grow by accretion, pulling in gas from their surroundings. As gas falls toward a black hole, it doesn't fall straight in. It has angular momentum, which causes it to spiral inward, forming an accretion disk. As gas spirals through the disk, friction between neighboring gas particles heats the gas to millions of degrees. This hot gas emits intense radiation, primarily in X-rays and ultraviolet light. The radiation from the accretion disk is so intense that it creates outward pressure on the surrounding gas. This is called radiation pressure, and it's the same force that causes comet tails to point away from the sun. Photons carry momentum, and when they hit gas particles, they transfer that momentum, pushing the gas outward. For a black hole, accreting gas, radiation pressure limits how fast the black hole can grow. If the accretion rate is too high, the radiation pressure becomes so strong that it blows away the infalling gas, shutting off the accretion. This maximum accretion rate is called the Eddington limit, named after British astronomer Arthur Eddington, who first calculated it in the 1920s. For a black hole, with the mass of our Sun, the Eddington limit corresponds to accreting about 1/1,000,000th of a solar mass per year. For a 100 solar mass black hole, the limit is about 1/10,000th of a solar mass per year. These seem like tiny amounts, but over millions of years, they add up. If a stellar mass black hole accretes at the Eddington limit continuously for 1 billion years, it can grow significantly. But here's the problem. Even accreting at the Eddington limit, which is the absolute maximum rate, it takes too long to grow from 100 solar masses to 1 billion solar masses. The universe is about 13.8 billion years old. The first stars formed a few 100 million years after the Big Bang, about 13.5 billion years ago. These first stars were different from stars today. They formed from primordial gas that contained only hydrogen, helium, and trace amounts of lithium. No heavy elements like carbon, oxygen, or iron, because those elements hadn't been created yet. Without heavy elements, these first stars couldn't cool their gas clouds as efficiently as modern stars can. So they tended to be much more massive, perhaps hundreds of times the mass of our Sun. When these massive stars exhausted their nuclear fuel and collapsed, they would have formed black holes, creating the seeds for future supermassive black holes. Let's say one of these first stars formed a black hole with a mass of 100 times the Sun's mass. This black hole starts accreting gas at the Eddington limit immediately. How long would it take to reach 1 billion solar masses? We can calculate this using exponential growth. At the Eddington limit, a black hole's mass doubles approximately every 50 million years. This is called the Eddington time. To go from 100 solar masses to 1 billion solar masses requires growing by a factor of 10 million. That's about 23 doubling times. 23 times 50 million years equals 1.15 billion years. So even in the best-case scenario, accreting continuously at the maximum rate with no interruptions, it would take over 1 billion years for a stellar mass black hole to grow into 1 billion solar mass, supermassive black hole. But astronomers have detected quasars, supermassive black holes actively feeding in the early universe at redshifts corresponding to when the universe was only 600 million years old. Some of these quasars have masses of billions of solar masses. That's not enough time for a stellar mass black hole to grow to billions of solar masses through accretion alone, even at the Eddington limit. The math simply doesn't work, and it gets worse. Black holes don't accrete continuously at the Eddington limit. In reality, the gas supply varies. Sometimes there's a lot of gas available, and the black hole feeds rapidly. Other times, there's little gas, and accretion slows down or stops entirely. The duty cycle, the fraction of time a black hole spends actively accreting, is probably much less than 100%. If a black hole only accretes 10% of the time, it would take 10 times longer to grow, making the timeline problem even worse. Additionally, some of the mass that falls toward the black hole doesn't actually make it in. Powerful jets and winds from the accretion disk can blow gas away, reducing the effective accretion rate below the Eddington limit. All of these factors make it even harder to explain how supermassive black holes grew so quickly in the early universe. So, there must be another mechanism. Intermediate mass black holes could be the missing link. If black holes can form with masses of thousands of solar masses, rather than just tens or hundreds, then they have a head start. They can grow into supermassive black holes much faster. A black hole that starts with a mass of 10,000 solar masses only needs to grow by a factor of 100 to reach 1,000,000 solar masses, rather than growing by a factor of 10,000 from a 100 solar mass seed. This dramatically reduces the time required. But how would intermediate mass black holes form? One possibility is that they form in dense star clusters, regions where stars are packed so closely together that they collide and merge. In the early universe, star clusters might have been much denser than they are today. If stars in these clusters collided and merged, they could create very massive stars, hundreds of times the mass of the Sun. These massive stars would burn through their fuel quickly and collapse to form intermediate mass black holes. Another possibility is that intermediate mass black holes form directly from the collapse of massive gas clouds in the early universe, without going through a star phase at all. In the early universe, gas clouds could have been much more massive than they are today, perhaps because the gas was less enriched with heavy elements. If a sufficiently massive gas cloud collapsed, it might form a black hole directly, bypassing the star formation process. These are called direct collapse black holes, and they could have masses of thousands or even tens of thousands of solar masses right from the start. But until now, we've had very little evidence that intermediate mass black holes actually exist. There have been a few candidate detections, but nothing definitive. Some globular clusters, dense spherical collections of old stars, appear to have intermediate mass black holes at their centers, based on the motions of stars in the cluster. And there have been a few detections of gravitational waves from merging black holes with masses in the intermediate range. But these detections are tentative, and there's debate about whether they represent true intermediate mass black holes or just the high mass end of the stellar mass black hole population. Webb's observations might change that. If the objects Webb detected around Sagittarius A really are intermediate mass black holes, it would confirm that these objects exist, and it would give us a laboratory to study how they behave. We could watch them interact with stars, watch them merge with each other, and watch them feed on gas. This would revolutionize our understanding of how supermassive black holes grow. It would show that black holes don't just grow by slowly accreting gas. They grow by consuming other black holes, including intermediate mass ones. Sagittarius A itself might have grown to its current mass of 4 million solar masses by merging with dozens or hundreds of intermediate mass black holes over billions of years. Each merger would have added mass to Sagittarius A and would have emitted gravitational waves that rippled through space-time. If we could detect these gravitational waves, it would confirm the merger scenario. But gravitational waves from mergers in the past have long since passed us, and we can't observe them directly. we can only infer that they happened based on the current mass and properties of Sagittarius A. And if intermediate mass black holes exist around Sagittarius A, they probably exist around other supermassive black holes too. This could be a universal mechanism, the primary way that supermassive black holes grow. Every supermassive black hole might be surrounded by a population of smaller black holes, intermediate mass and stellar mass, that it gradually consumes over cosmic time. This would explain how supermassive black holes can grow so quickly in the early universe. They start as intermediate mass black holes, perhaps formed from direct collapse, and then grow rapidly by merging with other intermediate mass black holes and by accreting gas. But we need more observations to confirm this. Webb has given us tantalizing hints, but we need follow-up studies to determine whether these objects really are intermediate mass black holes or something else. Future observations will track their orbits more precisely, measuring how they move over time. By watching how these objects interact with nearby stars, we can estimate their masses more accurately. If their masses fall in the intermediate range, and if their orbits are consistent with black holes rather than stars, it would strongly support the black hole interpretation. We'll also look for other signatures, like gravitational waves from merging intermediate mass black holes. The next generation of gravitational wave detectors, like the Laser Interferometer Space Antenna, or LISA, will be sensitive to lower frequency gravitational waves than current detectors. These lower frequency waves are produced by mergers of intermediate mass and supermassive black holes. If LISA detects gravitational waves from mergers in the galactic center, it would provide direct evidence of intermediate mass black holes. And we'll continue to refine our models of black hole growth, incorporating the new data from Webb and other telescopes. By comparing observations with simulations, we can test different scenarios and determine which mechanisms are most important for growing supermassive black holes. Let's step back and think about what all of this means. Every single one of Webb's discoveries around Sagittarius A contradicts what we thought we knew. Stars forming where they shouldn't. Water molecules surviving in conditions that should destroy them. Ionized gas with no apparent energy source. Intermediate mass, black holes hiding in plain sight. A dormant black hole surrounded by fuel, cycling through active and dormant phases on timescales of centuries. Each of these discoveries on its own would be significant. Together, they represent a complete overturning of our understanding of what happens in the most extreme environments in the universe. Here's why this matters. Black holes aren't just exotic objects that sit at the centers of galaxies doing nothing. They're active players in galactic evolution. When a supermassive black hole feeds, it releases enormous amounts of energy. This energy heats the surrounding gas, preventing it from cooling down and collapsing to form new stars. In effect, an active black hole can shut down star formation across an entire galaxy. This is called AGN feedback, active galactic nucleus feedback, and it's thought to be one of the main mechanisms that regulates how galaxies evolve. Without AGN feedback, galaxies would form stars too quickly, using up all their gas in a few billion years and leaving nothing for future generations. Simulations of galaxy formation that don't include AGN feedback produce galaxies that are too massive and too blue, meaning they're forming too many stars. These simulations don't match the observed properties of real galaxies. But when AGN feedback is included in the simulations, the results match observations much better. The feedback slows down star formation, preventing galaxies from becoming too massive, and it enriches the intergalactic medium with heavy elements by blowing gas out of galaxies. But with AGN feedback, star formation is slowed down, stretched out over longer timescales, allowing galaxies to continue forming stars for tens of billions of years. This creates galaxies that look like the ones we observe, with a mix of old and young stars, and with star formation rates that decline gradually over cosmic time. The problem is, we don't fully understand how AGN feedback works. We don't know what triggers a black hole to become active. We don't know what determines how much energy it releases. We don't know how that energy couples to the gas in the galaxy. We don't know how efficiently the feedback works, or whether it's the same in all galaxies or varies depending on the galaxy's properties. These are critical questions because AGN feedback is now incorporated into every major galaxy formation simulation. Without AGN feedback in the models, the simulations fail to reproduce the observed universe. They produce galaxies that are too massive, too blue, and forming stars too rapidly. But the feedback is implemented as a simple prescription, a mathematical formula that approximates a complex physical process we don't fully understand. If our understanding of the underlying physics is wrong, our simulations might be producing the right results for the wrong reasons. And that means our predictions about how galaxies will evolve in the future might be unreliable. Webb's observations of Sagittarius A are giving us clues. The fact that the black hole is dormant, despite being surrounded by fuel, tells us that there's some mechanism regulating when it feeds. It's not just a matter of gas availability. There's gas there, spiraling around the black hole, but it's not falling in. Something is preventing it, or at least slowing it down. Maybe it's the rotation of the gas, which creates angular momentum that resists infall. Maybe it's magnetic fields in the disk, which can transport angular momentum outward, allowing some gas to fall in while preventing the rest. Or maybe it's feedback from the black hole itself, even in its dormant state, producing winds or jets that blow gas away. We don't know. The evidence of past activity 300 to 400 years ago tells us that the transition between dormant and active states can happen relatively quickly on human timescales, not just cosmic ones. This is important because it means we might be able to observe these transitions in real time. If Sagittarius A becomes active again in the next few decades or centuries, we'll be able to watch the process unfold, tracking how the black hole's luminosity increases, how the gas distribution changes, and how the surrounding galaxy responds. This would provide invaluable data for understanding AGN feedback. And the presence of young stars forming near the black hole tells us that even in the presence of an active black hole, star formation can still happen under the right conditions. The feedback isn't total. It doesn't shut down all star formation everywhere. Instead, it's more nuanced, affecting different regions differently depending on the local conditions. In some regions, the feedback might be strong enough to completely suppress star formation. In other regions, perhaps shielded by dense gas clouds or located at greater distances from the black hole, star formation can continue despite the feedback. This complexity is important. It tells us that AGN feedback isn't a simple on-off switch that either allows or prevents star formation. It's a gradient, a continuum, with different strengths in different places. And the details matter. The exact strength of the feedback, how it varies with distance from the black hole, how it interacts with the galaxy's gas distribution, all of these factors determine the feedback's overall effect on the galaxy. These observations are forcing us to refine our models of AGN feedback. We can't just assume that an active black hole shuts down all star formation. The reality is more complex, more nuanced. Star formation and black hole activity are intertwined, affecting each other in ways we're only beginning to understand. The black hole regulates star formation through its feedback. But star formation also affects the black hole by determining how much gas is available for accretion. It's a two-way relationship, a feedback loop in the truest sense. And understanding this feedback loop is crucial for understanding how galaxies evolve. There's also the question of how common these phenomena are. Is Sagittarius A unusual, or is what we're seeing typical of supermassive black holes? This is a critical question, because Sagittarius A is just one example. If it's unusual, then Webb's discoveries might not tell us much about black holes in general. They might be specific to Sagittarius A's unique circumstances, perhaps related to its particular mass, or the properties of the Milky Way, or something else that makes it atypical. But if what we're seeing around Sagittarius A is common, if most or all supermassive black holes are surrounded by similar environments, then these discoveries have universal implications. They tell us something fundamental about how black holes work, not just in the Milky Way, but everywhere. We don't know yet. Sagittarius A is the closest supermassive black hole to us, which is why we can study it in so much detail. At 26,000 light-years away, it's close enough that Webb can resolve individual stars and gas clouds in the galactic center, measuring their positions, velocities, and properties with exquisite precision. Other supermassive black holes are much farther away, making them harder to study. The nearest large galaxy, Andromeda, is about 2.5 million light-years away, roughly 100 times farther than Sagittarius A. At that distance, Webb's resolution isn't good enough to see individual stars near the central black hole. We can see the galaxy as a whole. We can measure the total light from its center, but we can't pick out individual objects the way we can in the Milky Way. For galaxies beyond the local group, the distances become even more daunting. But it's just one example. To understand black holes in general, we need to study many of them. We need a large sample of observations, covering black holes of different masses in different types of galaxies at different stages of activity. Only then can we determine which features are common and which are unique. Only then can we separate the universal principles from the special cases. Webb is starting to do that. It's observing the centers of other galaxies, looking for similar phenomena. These observations are challenging because most galactic centers are much farther away than Sagittarius A, but Webb's capabilities make them possible. The telescope can detect faint objects at enormous distances, and its infrared vision can penetrate dust in other galaxies just as it does in the Milky Way. These observations are still in progress, and it will take years to analyze all the data, but early results are promising. Preliminary data from a handful of nearby galaxies suggests that the phenomena Webb observed around Sagittarius A are not unique. Early results suggest that what we're seeing around Sagittarius A is not unique. Other galactic centers show evidence of star formation in extreme environments, mysterious ionized gas, and possible intermediate mass black holes. One galaxy, called NGC 1068, has a supermassive black hole with a mass of about 15 million solar masses. Webb observations of this galaxy revealed young stars forming within a few light-years of the black hole, similar to what we see around Sagittarius A. Another galaxy, called M87, has a much more massive black hole, about 6.5 billion solar masses, and it's currently active, with a prominent jet extending thousands of light-years into space. Webb observations of M87's galactic center are ongoing, but preliminary results suggest a complex environment with clumpy gas structures and possible intermediate mass black holes. This suggests that these phenomena are common, perhaps universal. Every supermassive black hole might be surrounded by a chaotic, dynamic environment where stars form and die, where gas spirals inward and gets blown outward, where smaller black holes lurk and occasionally merge with the central monster. If that's true, it means we need to completely rethink how galaxies work. The galactic center isn't a passive, stable region. It's an active, evolving system that plays a crucial role in shaping the galaxy as a whole. The black hole at the center isn't just sitting there. It's regulating star formation, enriching the gas with heavy elements through its jets and winds, and growing over time by accreting gas and merging with other black holes. All of these processes affect the galaxy's evolution. Let's talk about the detection methods, because understanding how Webb made these discoveries helps us appreciate just how difficult this was. Infrared astronomy is hard. Infrared light is heat radiation. Everything warm emits infrared light. That includes the telescope itself. If the telescope is warm, it will emit so much infrared light that it drowns out the faint infrared signals from distant objects. To solve this problem, Webb operates at incredibly cold temperatures. The telescope is kept at about -390 degrees Fahrenheit, just 50 degrees above absolute zero. Absolute zero is the lowest possible temperature, the point at which all molecular motion stops. It's -459.67 degrees Fahrenheit, or 0 Kelvin. At 50 degrees above absolute zero, Webb is colder than the coldest natural environments in the solar system. It's colder than the surface of Pluto, colder than the interstellar medium, colder than almost anything except the cosmic microwave background itself. This extreme cooling is achieved using a massive sunshield the size of a tennis court. The sunshield is made of 5 layers of a material called kapton, a thin, reflective film that's incredibly effective at blocking heat. Each layer is separated from the next by a gap, creating an insulating barrier. The sunshield blocks light and heat from the sun, Earth, and Moon, allowing the telescope to cool down. On the sun, facing side of the sunshield, the temperature is about 185 degrees Fahrenheit, hot enough to boil water. On the opposite side, where the telescope sits, the temperature is -390 degrees Fahrenheit. This temperature difference of over 500 degrees is maintained by the sunshield's design. At these temperatures, Webb's own infrared emission is minimized, allowing it to detect faint infrared signals from space. But even with this cooling, detecting objects around Sagittarius A required pushing Webb to its limits. The galactic center is bright in infrared light. There are millions of stars there, all emitting infrared radiation. The combined light from all these stars creates a glare that makes it difficult to see individual objects. It's like trying to spot a single candle flame in the middle of a brightly lit stadium. To see through this glare and detect individual objects required extremely sensitive instruments and sophisticated data processing techniques. Webb's near-infrared camera, or NIRCam, was the primary instrument used for these observations. NIRCam is the most sensitive infrared camera ever built. It can detect individual photons of infrared light, counting them one by one to build up an image. It can detect infrared light with wavelengths between 0.6 and 5 microns, which corresponds to near-infrared, the part of the infrared spectrum closest to visible light. At 0.6 microns, NIRCam's sensitivity extends just into the visible red, allowing it to see the transition from visible to infrared light. At 5 microns, it's deep into the infrared, detecting heat radiation from warm objects. NIRCam has a resolution of about 0.1 arcseconds, which is incredibly sharp. An arcsecond is 1/3600th of a degree. To put that in perspective, the full moon in the sky is about half a degree across, or 1,800 arcseconds. 0.1 arcseconds is tiny, smaller than the apparent size of a coin viewed from several miles away. At the distance of Sagittarius A, 26,000 light-years, this resolution allows Webb to distinguish objects separated by about 0.02 light-years, or roughly 1,240 astronomical units. 1 astronomical unit is the distance from Earth to the Sun, about 93 million miles. So Webb can distinguish objects that are about 115 billion miles apart at the galactic center. That sounds like a lot, but remember, the region around Sagittarius A is packed with millions of stars. Stars near the galactic center are separated by distances of only a few light-years on average, and in the densest regions, they can be as close as a few hundredths of a light-year apart. Being able to pick out individual stars and gas clouds from this crowded field required not just high resolution, but also careful planning. The observations were done in multiple infrared wavelengths, allowing astronomers to distinguish different types of objects based on their infrared colors. Young stars, which are hot, appear bright in shorter infrared wavelengths. They emit a lot of energy in the near-infrared, around 1 to 2 microns. Cooler, older stars appear bright in longer wavelengths. Red giants and red dwarfs, for example, emit most of their light in the mid-infrared, around 3 to 5 microns. Gas and dust emit infrared light at specific wavelengths depending on their temperature and composition. Hot gas emits a continuum of infrared radiation, while cooler dust emits at specific wavelengths corresponding to the vibrational modes of the molecules in the dust grains. By combining images taken at different wavelengths, astronomers could identify individual stars, measure their temperatures and ages, and map out the distribution of gas and dust. This technique is called multi-wavelength imaging, and it's one of the most powerful tools in modern astronomy. The data processing was equally challenging. The raw images from Webb contained millions of stars, all blending together in a confusing jumble. Each star appears as a point of light, but because the stars are so close together, their light overlaps, creating a complicated pattern. Sophisticated algorithms were needed to separate individual stars, measure their positions and brightnesses, and track their motions over time. This process is called photometry, and it involves fitting mathematical models to the light distribution in the image to determine where each star is and how bright it is. This required comparing Webb's observations with earlier observations from other telescopes, looking for stars that had moved or changed brightness. Stars near Sagittarius A are moving rapidly, orbiting the black hole with periods ranging from a few years to a few thousand years. By comparing images taken at different times, astronomers can track the motion of individual stars, measuring their orbits and using that information to map out the gravitational field of the black hole. The ionized gas was detected using spectroscopy. Webb's near-infrared spectrograph, or NIRSpec, can split infrared light into its component wavelengths, creating a spectrum. A spectrum is like a barcode, showing exactly which wavelengths of light are present and how bright they are. Different atoms and molecules emit and absorb light at specific wavelengths, creating a fingerprint that reveals what the gas is made of and what physical conditions it's experiencing. For example, hydrogen emits light at specific wavelengths, corresponding to transitions between different energy levels in the atom. When an electron in a hydrogen atom jumps from a higher energy level to a lower one, it emits a photon with a specific wavelength. These wavelengths are characteristic of hydrogen, and they can be used to identify hydrogen in distant gas clouds. By analyzing the spectra of gas clouds around Sagittarius A, astronomers could determine that the gas was ionized, measure its temperature and density, and identify the presence of molecules like water. The width and shape of the spectral lines also provide information. If the gas is moving, the spectral lines are Doppler shifted, moved to longer or shorter wavelengths, depending on whether the gas is moving away from us or toward us. If the gas is hot, the spectral lines are broadened because the atoms are moving at high speeds, creating a range of Doppler shifts. All of this information is encoded in the spectrum, waiting to be decoded by astronomers. The intermediate mass black holes were detected indirectly by observing their gravitational effects on nearby stars. If a star's orbit is being perturbed by an unseen massive object, that object is likely a black hole. By tracking the orbits of multiple stars and looking for anomalies, deviations from the expected paths, astronomers could infer the presence of hidden black holes and estimate their masses. This technique is called dynamical modeling, and it's been used successfully to detect black holes in other contexts, including the discovery of Sagittarius A itself. The idea is to build a mathematical model of how stars should move under the influence of the black hole's gravity, and then compare that model to the observed motions. If the observed motions don't match the model, it means there's additional mass somewhere that the model didn't account for. By adjusting the model to include this additional mass, and by comparing the adjusted model to the observations, astronomers can determine where the hidden mass is and how much there is. All of this required months of observations and years of data analysis. The results we're discussing tonight represent the work of hundreds of astronomers around the world, collaborating to make sense of Webb's observations. Teams of scientists analyzed the data, built models, ran simulations, wrote papers, and peer-reviewed each other's work. This is how modern astronomy works. It's a collaborative effort, with scientists from different institutions and different countries working together to push the boundaries of human knowledge. And this is just the beginning. Webb is continuing to observe Sagittarius A, and with each new observation, we're learning more. The telescope is scheduled to observe the galactic center multiple times over the next few years, tracking changes over time and building up a detailed picture of the environment around the black hole. Now, let's talk about the future. What happens next? What will trigger Sagittarius A's next active phase? We don't know for sure, but there are clues. Active phases are likely triggered by a sudden influx of gas, a large amount of material falling toward the black hole all at once. This could happen if a star wanders too close to the black hole and gets tidally disrupted, torn apart by the black hole's gravity. When a star is disrupted, its material forms a temporary accretion disk around the black hole, and the black hole feeds voraciously for a few months or years. This produces a bright flare called a tidal disruption event. Tidal disruption events are rare but spectacular. When a star gets too close to a black hole, the tidal forces become strong enough to overcome the star's own gravity, which holds it together. The side of the star facing the black hole feels a stronger pull than the far side, stretching the star into a long filament. Eventually, the star is torn apart completely, and its material spreads out along its orbit, forming a stream that wraps around the black hole. As this stream of gas falls into the black hole, it heats up and emits intense radiation, creating a bright flare that can outshine the entire galaxy for a few months. Sagittarius A might experience a tidal disruption event every few thousand years on average. The rate depends on the density of stars near the black hole and their orbital dynamics. In the dense environment near Sagittarius A, where millions of stars orbit within a few light years, tidal disruption events are expected to be relatively common on cosmic timescales. The last one might have been the outburst 300 to 400 years ago, though we can't be certain. The evidence suggests a major outburst happened at that time, but we don't know what caused it. It could have been a tidal disruption event, or it could have been something else, like a gas cloud falling in. If so, the next one could happen any time in the next few thousand years, or it could happen tomorrow. We have no way to predict it. Stars near Sagittarius A are on chaotic orbits, and predicting when one will wander too close to the black hole is essentially impossible. We can calculate the average rate, but we can't predict individual events. Another possible trigger is a gas cloud wandering too close. There are several large gas clouds orbiting near Sagittarius A, and occasionally one gets close enough to be disrupted by the black hole's gravity. In 2014, a gas cloud called G2 made a close approach to Sagittarius A. Astronomers predicted that the cloud would be torn apart and that the black hole would feed on it, producing a bright flare. Observations were planned. Telescopes were aimed at the galactic center, and everyone waited to see what would happen, but nothing happened. The cloud survived, passing by the black hole relatively unscathed. This was surprising and disappointing, and it showed us that we still don't understand the dynamics of gas around black holes as well as we thought. Why did G2 survive? There are several possibilities. Maybe the cloud was denser than expected, allowing it to hold together against the tidal forces. Maybe it had a star at its core, providing additional gravitational binding. Or maybe our models of the cloud's trajectory were wrong, and it didn't pass as close to the black hole as we calculated. But other gas clouds are out there, and future close approaches might have different outcomes. Webb is monitoring several gas clouds near Sagittarius A, tracking their positions and velocities. If one of them starts to fall toward the black hole, we'll be watching. There's also the possibility of a more gradual build-up. Gas is constantly trickling towards Sagittarius A from the surrounding region. Stellar winds from nearby stars, gas shed by dying red giants, material from the interstellar medium, all of it gradually makes its way inward. Most of this gas doesn't make it all the way to the black hole. It gets blown away by stellar winds, heated by radiation, or otherwise dispersed. The accretion disk around Sagittarius A is fed by this trickle of gas, but the rate is low, which is why the black hole is currently dormant. But over time, gas can accumulate in the accretion disk. If enough gas builds up, the disk might become unstable, triggering a sudden increase in the rate at which gas falls into the black hole. This is called a thermal instability, and it's thought to be one of the mechanisms that can trigger outbursts in black holes. The idea is that as gas accumulates in the disk, it heats up due to friction. At low densities, the disk is relatively cool and stable, but if the density increases past a certain threshold, the disk can suddenly transition to a hot, unstable state where gas falls inward much more rapidly. This transition could trigger an active phase, causing the black hole to suddenly become much brighter. We're watching and waiting. Webb and other telescopes are monitoring Sagittarius A continuously, looking for any signs of increased activity, changes in brightness, changes in the spectrum of the accretion disk, changes in the distribution of gas. All of these could be early warning signs of an impending outburst. When the next active phase happens, we'll be ready to observe it in unprecedented detail. We'll be able to watch in real time as the black hole lights up, as jets form and blast outward, as the surrounding gas is heated and ionized. We'll see the accretion disk brighten, the X-ray emission increase, and the jets extend outward into space. This will give us invaluable data on how black holes feed and how they affect their surroundings. We'll be able to test our models of accretion, compare observations to simulations, and refine our understanding of AGN feedback. In the meantime, Webb is continuing to make new discoveries. Every observation reveals something unexpected, something that challenges our understanding. The field is moving incredibly fast right now. Papers are being published every few months, with new findings, new puzzles, new mysteries to solve. We're in a golden age of black hole astronomy, a time when our observational capabilities have finally caught up with our theoretical ambitions. For decades, we've had theories about how black holes work, but we lacked the tools to test them. Now, with Webb and other advanced telescopes, we can finally observe black holes in the detail needed to test our ideas. And what we're finding is that reality is far more complex and interesting than we imagined. Let's come back to the central paradox: cosmic fertility in a sterile environment. This is the through line that connects all of Webb's discoveries. In a region where nothing should survive, where radiation should sterilize everything, where tidal forces should rip apart any structure, we find stars forming, water molecules existing, complex chemistry happening. It's as if nature refuses to be constrained by our theoretical predictions. Our models say that star formation near a black hole is impossible, but nature finds a way. Our models say that water molecules should be destroyed instantly, but there they are, glowing in Webb's infrared observations. Our models say that ionized gas requires an energy source, but the gas is glowing anyway. Wherever there's an opportunity for complexity, for structure, for something new to emerge, nature finds a way. This tells us something profound about the universe. Extreme environments aren't necessarily dead zones. They're not lifeless, sterile regions where nothing can happen. Instead, they're dynamic, evolving, full of surprises. They're places where the laws of physics are pushed to their limits, where conditions are so extreme that new phenomena emerge. The universe is more resilient, more creative than we give it credit for. It's not content to settle into simple, uniform states. It creates complexity wherever it can, building structure out of chaos, order out of randomness. And this has implications beyond black holes. If star formation can happen in the chaotic environment around Sagittarius A, where else might it be happening? Are there stars forming in other extreme environments we thought were sterile? Around neutron stars, with their intense magnetic fields and rapid rotation, in the jets of active galaxies, where gas is being blasted outward at nearly the speed of light, in the debris of supernovae, where a star has just exploded and scattered its material across space. All of these environments are extreme, with conditions that seem hostile to star formation. But if we've learned anything from Webb's observations of Sagittarius A, it's that our intuitions about what's possible can be wrong. Nature is full of surprises. If water can exist near a black hole, what about other molecules? Could complex organic chemistry happen in such environments? Organic molecules are the building blocks of life. They include simple molecules like methane and formaldehyde, and more complex ones, like amino acids and sugars. On Earth, these molecules are produced by living organisms, but they can also form through non-biological processes. In space, organic molecules have been detected in molecular clouds, in the atmospheres of planets, in comets and asteroids, and even in the interstellar medium. They form through chemical reactions involving carbon, hydrogen, oxygen, nitrogen, and other elements. Could they form near a black hole? Could there be prebiotic molecules, the building blocks of life, forming in places we never thought to look? It seems unlikely, but a few years ago, finding water near a black hole seemed unlikely too. These questions sound far-fetched, but a few years ago, the idea of stars forming near a black hole sounded far-fetched too. Webb has shown us that the universe is full of surprises, that our theories are incomplete, that there's still so much we don't know. And that's exciting. That's why we do science. Not to confirm what we already believe, but to discover what we don't know, to be surprised, to be proven wrong, and to learn from our mistakes. Every time we point a telescope at the universe and find something unexpected, we get a little closer to understanding how it really works. We refine our models, update our theories, and build a more accurate picture of reality. Webb's observations of Sagittarius A are a perfect example of this. We thought we knew what to expect. A dormant black hole, surrounded by old stars, with maybe some gas trickling inward. The galactic center should be a relatively quiet place, with the black hole sitting there passively, occasionally consuming a bit of gas, but otherwise not doing much. Instead, we found young stars, water molecules, ionized gas, and candidate intermediate mass black holes. Every assumption was challenged. Every prediction was overturned. The galactic center is not quiet. It's a hive of activity, with stars forming, gas swirling, and black holes lurking in the shadows. And now we're scrambling to make sense of it all, to build new models, to explain what we're seeing. Theorists are going back to their simulations, adding new physics, trying to reproduce Webb's observations. Observers are planning new observations, looking for additional evidence, testing the new theories. This is how science progresses. Not smoothly, not predictably, but in fits and starts, with sudden leaps forward when new data forces us to reconsider everything. It's messy, it's chaotic, and it's absolutely thrilling. Let me leave you with one final thought. Sagittarius A is 26,000 light-years away. When we look at it, we're not seeing it as it is now. We're seeing it as it was 26,000 years ago, long before human civilization existed. The light that Webb is detecting left the black hole during the last ice age, when woolly mammoths still roamed the earth, when humans were just beginning to develop agriculture and settle into permanent communities. At that time, humans were hunter-gatherers, living in small groups, following herds of animals and gathering plants for food. They had stone tools, they had fire, they had language, but they hadn't yet invented writing or cities or any of the trappings of modern civilization. And yet, at that same moment, 26,000 years ago, light was leaving Sagittarius A, carrying information about the black hole's environment. That light traveled through space for 26,000 years, crossing the galaxy, passing through clouds of gas and dust, until finally, in the year 2023, it arrived at Webb's mirror and was captured by the telescope's detectors. Everything Webb is showing us, the young stars, the water molecules, the ionized gas, all of it, happened 26,000 years in the past. By now, in the present moment, those stars have aged. Some of them might have already died in supernova explosions, scattering their material across the galaxy. The water molecules have long since been destroyed and reformed countless times. The gas has spiraled farther inward toward the event horizon, or been blown outward by stellar winds. And Sagittarius A itself might be in a completely different state. Perhaps it's in the middle of an active phase that we won't see for another 26,000 years. Or perhaps it's still dormant, unchanged from what Webb observed. We can't know. This is the nature of astronomy. We're always looking into the past, observing light that has traveled for thousands, millions, or even billions of years to reach us. We can never see the universe as it is right now, only as it was. For distant galaxies billions of light years away, we're seeing them as they were billions of years ago, when the universe was much younger. Some of those galaxies might not even exist anymore, destroyed in collisions or transformed beyond recognition. And yet, this doesn't diminish the value of what we're learning. The laws of physics are the same everywhere and at all times. What was happening around Sagittarius A 26,000 years ago tells us about how black holes work, how stars form, how galaxies evolve. These are universal principles that apply not just to our galaxy, but to every galaxy in the universe, at every point in cosmic history. The physics of star formation is the same, whether it's happening now or 26,000 years ago. Gas clouds collapse under gravity when their self-gravity overcomes internal pressure. They fragment into smaller clumps as they collapse. Those clumps continue to contract, converting gravitational potential energy into heat. Eventually, the cores become hot enough for nuclear fusion to ignite, and stars are born. This sequence of events is universal, governed by the laws of thermodynamics and gravity. The details might vary depending on the composition of the gas, its temperature, or the external environment, but the fundamental process remains the same. The behavior of black holes is governed by the same equations. Einstein's general relativity, formulated over a century ago, describes how mass curves, space-time, and how that curvature creates what we perceive as gravity. These equations apply to every massive object, from planets to stars to black holes. They don't change over time. A black hole that formed 1 billion years ago follows exactly the same rules as a black hole forming today. The event horizon is always located at the Schwarzschild radius, determined solely by the black hole's mass. Light always follows geodesics, the straightest possible paths through curved space-time. Time always runs slower near massive objects. These aren't approximations or simplified models. They're precise mathematical descriptions of how reality works. The chemistry of water molecules follows the same rules. Hydrogen atoms have 1 proton and 1 electron. Oxygen atoms have 8 protons and 8 electrons. When 2 hydrogen atoms bond with 1 oxygen atom, they form a water molecule with a bent shape and specific properties. This happens the same way whether the reaction occurs on Earth, in interstellar space, or near a supermassive black hole. The bonds between the atoms are governed by quantum mechanics, by the electromagnetic force between charged particles, by principles that don't change based on location or time. By studying the past, we're learning about the present and the future. We're learning how the universe works, how it got to be the way it is, and where it's going. We're learning the fundamental laws that govern reality, laws that don't change with time or location. And we're learning that the universe is far stranger, far more complex, and far more beautiful than we ever imagined. It refuses to fit into the neat boxes we try to construct for it. Every time we think we understand how something works, new observations reveal unexpected complexities. Every time we build a theory that seems to explain everything, nature shows us phenomena that don't fit the theory. This isn't a flaw in our scientific method. It's a feature. It's how science progresses. We build models based on available data. We test those models with new observations, and when the observations don't match the predictions, we refine the models. Sometimes we refine them slightly, tweaking parameters or adding new terms to the equations. Sometimes we have to throw out the old models entirely and build new ones from scratch. The history of physics is filled with these revolutions. Newton's laws of motion and gravity worked beautifully for centuries, explaining everything from falling apples to planetary orbits. Then, observations of Mercury's orbit and experiments with the speed of light revealed tiny discrepancies. Einstein developed relativity to explain these discrepancies, and in doing so, revolutionized our understanding of space, time, and gravity. Quantum mechanics emerged from similar observations that classical physics couldn't explain. The blackbody radiation spectrum, the photoelectric effect, the stability of atoms, all pointed to something fundamentally new about how nature works at small scales. Now we're at another frontier. We have two incredibly successful theories, general relativity and quantum mechanics, that describe different aspects of reality with remarkable precision. But they don't fit together cleanly, and observations like Webb's discoveries around Sagittarius A are showing us phenomena that push both theories to their limits. Every new observation reveals new mysteries, new puzzles to solve, new questions to answer. And that's what makes this work so rewarding. The James Webb Space Telescope has given us a gift. It has shown us that even in the most extreme environment we can observe, at the edge of a supermassive black hole, 26,000 light-years away, buried behind an impenetrable wall of dust, nature finds a way. Stars are born where they shouldn't exist. Water survives where it should be destroyed. Chemistry happens in the most hostile environment imaginable. And black holes, those cosmic monsters that we thought we understood, are revealing themselves to be far more mysterious than we ever realized. They're not simple objects that just sit there, consuming whatever falls in. They're dynamic, evolving, surrounded by complex ecosystems of stars and gas and smaller black holes. They cycle between active and dormant states, regulating the evolution of their host galaxies. They grow by accreting gas and merging with other black holes, including intermediate mass ones. And they create environments where the laws of physics are pushed to their absolute limits, revealing new phenomena that we never predicted. This is just the beginning. Webb will continue observing Sagittarius A for years to come. Each observation will reveal new details, answer some questions, and raise new ones. We'll watch stars forming in real time, track gas as it spirals toward the event horizon, search for more intermediate mass black holes, and wait for the next active phase. And with each discovery, we'll rewrite the textbooks a little more. We'll refine our models, update our theories, and get a little closer to understanding how the universe really works. The heart of our galaxy is no longer a mystery, shrouded in dust. For the first time in history, we can see it clearly, in all its chaotic, violent, beautiful complexity. Thanks to Webb, we can finally see it clearly. And what we're seeing is forcing us to reconsider everything we thought we knew about black holes, star formation, and galactic evolution. The universe has spoken. It has told us that our theories were incomplete, that reality is stranger and more wonderful than we imagined. It has shown us that extreme environments are not sterile wastelands, but dynamic, evolving systems where new structures emerge and surprising phenomena occur. And now it's our job to listen, to learn, and to figure out what it all means. We're standing at the edge of a new understanding, looking out into a universe that's far more complex than we realized. Thank you for joining me on this journey into the heart of the Milky Way. If you found this exploration worthwhile, a like or subscribe would help this channel continue bringing you these deep dives into the cosmos. It really does make a difference, and it allows me to keep making these videos for curious minds like yours. And remember, the next time you look up at the night sky, you're looking at a universe full of mysteries, full of surprises, full of wonders we're only just beginning to understand. The stars you see are part of the Milky Way, our home galaxy, and at its center, invisible to your eyes, but revealed by Webb's infrared vision, sits Sagittarius A, a supermassive black hole, surrounded by impossible stars, mysterious gas, and secrets we're only now starting to uncover. 26,000 light-years away, hidden behind walls of cosmic dust, a cosmic drama is unfolding. Stars are being born in the most hostile environment imaginable. Water molecules are surviving against all odds. Intermediate mass black holes are lurking in the shadows. And a supermassive black hole is cycling through phases of activity and dormancy, shaping the evolution of our entire galaxy. The universe is stranger than we think. It's stranger than we can think. And that's what makes it so worth exploring. Every observation reveals something we didn't expect. Every discovery raises new questions. Every answer leads to deeper mysteries. This is the joy of science, the thrill of discovery, the wonder of understanding. We're living in an age where we can peer into the hearts of black holes, watch stars being born in impossible places, and detect molecules in the most extreme environments in the universe. We're living in an age where our telescopes can see farther and clearer than ever before, revealing a cosmos that's far stranger and more beautiful than our ancestors could have imagined. And we're just getting started. Webb has many more years of observations ahead of it, and each year will bring new discoveries, new surprises, new mysteries to solve. The universe is vast, ancient, and full of wonders, and we're fortunate enough to be living at a time when we can explore it, understand it, and marvel at it. Good night, and sleep well under the stars.